Hello, Franz here, Clay Manufacturing. This is going to be a quick-ish video on how to find feeds and speeds for my machine. And spoiler alert, there's no one size fits all. It's going to be very dependent on the diameter of your tool. What is your tool made of? Is it carbide, high-speed steel, cobalt? How many flutes is your tool? How long of flutes is your tool? Your stick out, your work holding, your material you're cutting, the rigidity of your machine, the horsepower of your machine. There's a lot of factors that go into feeds and speeds. I'll show you what I use to dial in feeds and speeds for my mini mill, or at least kind of to get me going. There's several websites I use for that. And so for our example, this is a 3/8 diameter. I believe it's a 1-inch flute length. I'm just going to pretend it's a 1-inch flute length. It's a 3 flute. It's a bright finish. It's an uncoated end mill. And so we're going to start there. And most times when you buy an end mill, it's got the part number, and each manufacturer has recommended feeds and speeds for the tooling. And so even though I might buy a tool from one manufacturer, I'll still kind of reference several other websites of a similar tool, just to kind of find like a baseline for me to start. And I've been a little sidetracked off my education videos because they're a whole lot of work. I haven't forgot about them. And also I've been kind of playing around making these little these little knives with stainless. So making these, this is annealed stainless steel. So this one is straight off the machine. This one is just through a vibratory tumbler a little bit. But why am I showing you this? Because I used Haas end mills. I pretty much buy Haas end mills for everything. And I used basically strictly Haas feeds and speeds for doing that stainless, and it was great. Let's get into what I'm showing you and why I have this up here. So I do have on my website feed, like the tool library. So this tool library that you can download. And I'm not really using it as a plug, but I want to show you something cool. So I'm going to go right click and I'll say edit. And when I'm looking at my feeds and speeds with an end mill, I'm looking at the feed per tooth, also the IPT, inch per tooth. So this is about 3.3 thou. So it's 3 thou, a little over 3 thou. So I'm paying close attention to that. And then I want to show you something else. I'm going to come to my select, and I have my clay mini mill aluminum. And if we do my T, did I say T3? It's my T2 on here. So it's my T2, it's my 3/8. So when I click on it, I have a product link right here. And I'm just going to click on here, and I'm going to follow that link. No, I don't work for Haas. This is the tooling I'm using. So this brings me to the exact end mill that I'm using. And Haas has really good speeds and feeds charts. So I'm going to click right here. And this side cutting HSM, it's kind of a newer strategy where it's small step overs, really fast linear feed rate, and relatively long depth of cut. So let's break it down. We're going to pretend we're using aluminum wrought alloy. And we're using our, let me zoom in a little bit. We're using our 3/8 end mill. So the inch per tooth, that feed per tooth, that's what I'm looking right here. So this is relatively high. And again, this is a small width of cut or step over, or optimal load as Fusion calls it, and a really high feed rate. And Haas also puts in a recommended RPM. So if you're using an SFM, your surface feet, your machinability of the material of 8,000, it's saying your inch per tooth can be 10 thou, but your RPM needs to be 81,000. I don't know about you, but I don't have an 81K spindle. So when a situation like this arises, you max out your RPM. So on mine it's 6K, so I'd max out my RPM, and then I'd try to adjust my linear feed rate to accomplish this 10.5 thou inch per tooth. Now there's some things we need to really pay attention to. We have to pay attention to our width of cut. And if you go down here, there's a little diagram. So side cutting, so this is the AE, and it gives you a little conversion, or a little formula. So if you're using these feeds and speeds, this side cutting HSM, you need to use these parameters. So let's pop out my calculator. I did some math. If we're doing a 3/8 end mill, we're going to do 0.05 times the diameter. for their recommended width of cut. So this is 0.05 times 0.375, enter. So that's a small step over. So the max step over, if you're using that, the feed and everything that pertains to this, sorry, it's like about 19th thou of your step over. And you do not want to exceed a depth of cut. So that's your AP. If you look on the lower left right there, you don't want to go more than 2 times the diameter. So if I clear this out, so my diameter again is 0.375 times 2. So it means with these feeds and speeds, the maximum depth of cut I can do is 3/4 of an inch. So that's a pretty good step down. That's the max. Now, on this one, this is incredibly fast, and I found on my mini mill that it doesn't work that well for me. I'm not willing to run my machine fast enough. Also, this strategy, you have to do tons and tons and tons of step overs to machine something. So I've actually been increasing my width of cut a little bit on my machine. And then before I hop on over to another website where I go to Guhring a lot. Guhring is a good website for feeds and speeds as well. But let's cruise down this one. So on these speeds and feeds, we have a more traditional side cutting. And so here, if I'm looking at the same tool diameter, the 3/8, you see how the chip load is drastically reduced. It's 4.5 thou. So on the other one, it was 0.010. This is 0.0045. And that is because if you look at the width of cut, the width of cut has increased a lot. So it's 0.5 times 0.375. That's the cutting tool diameter. And I'm going to say enter. So the width of cut is 0.1875. So that's how much it steps over in between steps. So you have a lot more engagement on the side of the tool. And if you notice, the depth of cut maximum decreases as well. So that's 1.5 times 0.375, enter. So the max with these settings, with this chip load, is a little more than 1/2 of an inch, where that other one was 3/4. And let's see. And then you see right here, it's still saying the RPM is 30K, which most of us don't have a 30K spindle. So on mine, I would max it out at 6,000 and start adjusting my linear feed rate to get here. However, my machine's not that rigid compared to like a bigger 8,000 plus pound machine. My machine's about 4,000 pounds. It's like just barely an industrial grade machine. And in fact, most people just laugh that it's a Haas, but for the money, it's awesome. So where do I go from here? Sorry, we're on here just for more. So this is for side cutting. When you're using the end mill and you're cutting on the side, let's see, when you're cutting on the side of a part like so. Now, if you're just slotting, let's see if I can do this. If you're just slotting like this, you have to reduce these feeds and speeds even more. And a lot of manufacturers, they will show you, here's this, slotting, and we're on the same one, and 3/8. So this is still the same chip load, I believe. It's 4.5 thou. However, you see they reduced the RPM on here. And the width of cut is 1 times the diameter because you're slotting the width of the diameter. So that's if you're just plowing this thing straight through material. And then the maximum depth you want to do, recommended, is between each pass, the maximum recommended depth is 1 times the diameter. So in this case, it'd be 1 times 0.375, which I'm barely smart enough to do that. So that's 0.375. So if you were doing a slot deeper than that, you'd have to go 0.375 deep and then continue until you get to your nominal value. And then let's go over to Guhring. So this is Guhring's website, Guhring. I really love their feeds and speeds. I probably use this one the most. And when I'm doing feeds and speeds, I'm bouncing between websites, kind of seeing, because you're going to have to machine, you're going to have to start somewhere. And let's see, Fusion, I'm going to say cancel. And a lot of times, if you're starting with your feed per tooth about 1 thou, that's really low. You probably don't want to go much lower than that, but it's really safe for a lot of machines. And in aluminum, most of the times, when you're side cutting, not drilling, side cutting with like an end mill, I'll max out my RPM and then just adjust my linear feed rate here to get my feed per tooth here. So they affect each other. And so I'll do it right now. So if I drop this down if I go cutting feed rate, let's go to 10 inches a minute. you see how it drastically reduces it. Now it's a half thou, and if I increase this to 100 inches a minute, you see now it's at 5 thou, and if I decrease my RPM, it's going to load that tool up more. So if I go from 6,000 RPM to 2,000 RPM, look at that, now I'm really loading it up. So it's generally safer in aluminum to have a higher RPM versus, like, you typically max out, you have a high RPM, so that way if your feed's not spot on, you're not loading the tool or the machine up as much, or if you get your offsets wrong. I usually see people when they're using a wobbler, they get their offset wrong by 100. They either add or subtract 100 thou in the wrong direction or forget altogether. So they're plowing that tool through material, and that's where I see a lot of problems. So when you have that RPM up and it's taking a bigger cut than you think, it's safer on the machine versus if you had a lower RPM. And that's aluminum. You get away with murder in aluminum. It's like glorified wood. So when you're doing your steels or harder material, you need to be pretty spot on with your feeds and speeds. Now, I'm back on the Guhring website. We're still talking about how I find my feeds and speeds. And Guhring's awesome. It breaks it down. It really simplifies it. It doesn't just show me the color. It gives me a description of the item. So I want aluminum, and then we'll kind of work our way to my tool that I have. I want my diameter and fractions, so I'm going to click on here. And this tool we're doing is 3/8. So yeah, I'm going to go update results. And let's see. So this, I know mine's, see, these have a coating on them. The one in my example does not. So we're right here, 3/8. This, my flute length right here, this is I2. It's saying 1 inch. So if I look down, this is my length of cut or flute length. That's 1 inch. And my overall length right here, I think that's an I1, yeah. That's the overall length is 2.5 inches. And my shank diameter, all right, everything looks good. And this is a 3 flute. So that's really close to the tool. It's a carbide tool, so it's really close. So we're just going to look at it. We're going to go to full details, and we're going to do some compare and contrast. And I'm going to come, and then it shows you everything this end mill's capable of, and this is the same as the one I just showed you in my hand. And right here, this shows you, so these colors and letters represent what material it is, and these show you what it's kind of designed for, and then these secondary are, okay, it's not specifically designed for this, but it can do it pretty good. And then this is not even selected because it is not meant for hardened steel or apparently chilled cast iron in this one. And I love these. This is just simplifies it so well for me. These are all good formulas. I have this written down in your notebook, RPM, so you can kind of look up the SFM, the machinability of a material, and kind of get what idea of RPM. It becomes a lot more important, like I said, with steels and hard materials. And look at this chart. So this is if I'm looking up for steels, but let's, right here, this is my 3/8 tool, so this is my diameter, and let's go on down. So this goes, okay, 60, 61, I'm right here on the lower left. I'm going to come over to this column. Let's scroll up. So 3/8, it's saying in 6061, the baseline chip load is 2 thou. Now check out what they do. So they have, if you're doing high-speed machining, so that's like the HSM strategy we just looked at Haas. So we've got a whole different little categories over here, and they even break it down even more. So if you read over here, this will tell you like finishing and stuff, and verify everything I'm saying. Like sometimes I look at my videos, I'm like, that was verbal diarrhea. I said the wrong thing. I didn't mean it, because sometimes my brain and mouth are not in sync. But verify what I'm saying. This says for finishing, use width of cut 0.01 to 0.1. So these ones would be your kind of your finishing strategies. So if we're looking at this, this shows my depth of cut and width of cut. So if I'm using this HSM, this would be like a finishing strategy. I usually use this 10%. So this is width of cut. And for this one, it's saying if I'm using this strategy right here, this is width of cut. This says my depth of cut can be no greater than 2 times the diameter of my tool. So let's just knock that one out of the park. So 2 times 0.375. So that means my step down is not more than 3/4 of an inch. And if I'm using this step over 0.1 times diameter, it means my step over 0.1 times 0.375, enter, is no greater than 0.375. So that's kind of, I usually, on my Haas mini mill, I usually use this, I use 10% of the cutter diameter as a rule of thumb. It's a pretty safe one. And then check this out though. So what's cool is, now here's a multiplication factor. If you're using this step over, you can multiply this chip load that we have down here, this 2 thou, you can multiply that chip load by this number. So I'm just roughly, it was about 2,000, a little more, let's say 0.002 times 2.3. And it's saying I can get away with about 4.5 thou if I'm no greater than 3/4 of an inch and my step over is no more than 0.375. So I like this one a lot. And then let's see, RPM. And so if you're doing that, you need to kind of, because this doesn't tell you your RPM. So if you're using this one I showed you, this is saying your SFM is, I believe, this column. Let's look. Nope, you're stupid. Where's my SFM? It's probably right in front of my eyeballs. Oh, it is. I'm sorry. This is the SFM right here. So it's showing, okay, that makes sense. Sorry. So this is 2050. And let's do our formula. So to find my RPM, I'm going to go like this. I'm going to go, what was it, 2050? I think it's 2050. If not, I'm close. 2050, divide the diameter, 0.375, enter. And then I'm going to say times 3.82, enter. So RPM of 20,000, 21,000. I don't have that. So what I'm going to do is max out my RPM and then adjust my linear feed rate to get to this the chip load that we calculated based on 2 thou multiplied by this multiplication factor. And since I'm on a Haas mini mill, I'm usually, you know, I'll do this 10% load, or I'll do this 10% for the width of cut. I'll do 0.1 times the diameter, and I'll just use, I won't do this multiplication factor. I'll just kind of use this as a baseline down here, this 2 thou chip load. It's really safe. And then if you're getting chatter, reduce your linear feed rate. If you can run it harder, if everything's looking good and smooth, you can try increasing your linear feed rate till you find what works for you. So this is a good website. I'm sure I'm kind of missing a lot of stuff, but dang it, I'm 17 minutes into this. And then IMCO, here's another one, IMCO feeds and speeds. I'm just going to click on one. And they have a pretty good speed and feed calculator as well. And then this has been acting goofy, but you go download PDF. And so again here, these have really good feed and speed charts. Here's like a 3/8 recommending 4.5 thou. And here's if you're doing slotting, if you're roughing around it, or if you're doing a finishing strategy. And while I'm here, so those are usually for when you're coming around the part, like those ones I was showing you for the side cutting and side milling HSM. Once you start getting inside here, you really need to reduce your linear feed rate because the surface speed of the tool is super fast when it's going around these corners. And when tools break, it's usually in the corners because they're loaded up. They're changing direction, they're increasing in engagement, and usually the prior pass didn't remove enough material, so it's super loaded up. And if you're trying to run your super high linear feed rate around the part that you're doing in here, you're probably going to break a tool or get excessive chatter. So maybe even start using your slotting feed rates in here. And what I'm looking at in these tool paths, so we were talking about calculating your width of cut. If you're doing an adaptive strategy, that is your optimal load. So we're looking at that optimal load. It's 0.375. So that's what I've been using on kind of my curriculum stuff. Sometimes if I'm unsure, I'll use that first Haas one I showed you where I do 0.05 times the diameter, so it's a really small step over. So let's kind of go over what really affects how your spindle is loaded up, how your tool is loaded up, how aggressive you're being. This optimal load can also be called your step over or your width of cut. This is extremely important. So always make sure you have your optimal load set to what I showed you in those charts. And then on your tool, cutting RPM, super important. Your cutting feed rate, super important. And your RPM and feed rate are affecting your feed per tooth. And in those charts, the feed per tooth is kind of That's my money. That's what I'm paying very close attention to. So I'm figuring out what feed I need, and usually maybe start in the 1 thou range and start working your way up when you're feeling confident with your setup. And because the ones they provide you are also baselines for more typical industrial big rigid machines. So if you got some big badass Mazak or something, you can probably far exceed what they're showing you, a real rigid machine. And that's about it. This has gone way, 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 way too long. I hope this helps, but it is very in-depth. This is just to get you started and to show you where I get started. I look at the feed per tooth, also known as the inch per tooth. I look at the step over right here, this optimal load or step over or width of cut, and my linear feed rates. These ramp feed rates, usually the Fusion defaults are pretty darn good where I don't go wild with them. And once I get comfortable with a program, then I'll start increasing those up until it kind of works for my machine. These are incredibly slow, but they're also incredibly safe. I haven't had a problem with their ramp or plunge feed rates at this point. All right, I hope that helps. Have a good one. Bye.